Now we're going to talk about metamorphism, alteration of rocks by temperature and pressure. The word itself, metamorphism, means a change in form. Now, some important aspects about metamorphism include the fact that the changes occur due to heat, pressure, and the chemical environment of the rocks. This alters the mineral composition and the texture of the crystals, and therefore making them metamorphic rock. Metamorphic changes occur in the solid state. This implies that there's no melting. That's mostly true. For our purposes, we'll say no melting. All of the changes occur in the solid state. The minerals are remade, reorganized, all in the solid state. No liquid. Most of this metamorphism occurs at depths between 10 and 30 kilometers, where the rock is hot, but not too hot. So today we're going to talk about the causes of metamorphism, the types of metamorphism, the types of texture we'll observe in metamorphic rocks, regional metamorphism and metamorphic grade, how metamorphic can we get, and the relationship between plate tectonics and metamorphism. Starting with the causes of metamorphism, we have the internal heat of the Earth. The radioactive decay of elements within the Earth generate heat. As we saw in previous lectures, that internal heat is going to influence pre-existing crystals. The internal pressure of the Earth is also going to influence pre-existing crystals. Under heat and pressure, the orientation as well as the chemistry may change. The fluid composition inside the Earth is going to be important, as it's going to add ingredients to the mix of pre-existing rocks and minerals. The temperature increases with depth, such that the further we go down into the Earth's crust, the more likely we're going to undergo a metamorphic regime in terms of temperature and pressure. Now, the rate of temperature increase as we go down into the Earth's crust is usually about 20 to 60 degrees centigrade per kilometer. At about 15 kilometers depth, the temperature is approximately 450 degrees. Looking at a cross-section of the United States from just south of Portland in Oregon over to, this is around close to Davenport, Iowa, we're going to take a look at how the temperatures change, therefore how the metamorphic environments may change. We're going to see pressure and temperature increase with depths in all regions. Starting with the west coast, we have a volcanic mountain belt, the Cascades in Oregon and Washington, up into British Columbia. In this location, the 1300 degree isotherm is about 50 kilometers down. This is the temperature at which almost everything is going to melt. Things that we see at the Earth's surface would melt. Now, here in the zone of plate extension, the Rocky Mountains, we see the 1300 degree isotherm is only about 30 kilometers deep. And in the ancient stable continental lithosphere underneath Iowa, we can see that the 1300 degree isotherm is about 150 kilometers down. So any material would have to be much further down below the Earth's surface to be metamorphosed in a continental interior, as opposed to in a zone of plate extension or a volcanic mountain belt, where metamorphic conditions are much closer to the surface. Other causes of metamorphism include the role of temperature. The role of temperature is such that the geothermal gradient is going to increase in temperature with depth, as we just saw. We can have a shallow geothermal gradient of 20 degrees increase per kilometer, or a fairly steep geothermal gradient of 50 degrees centigrade per kilometer of depth. Now, this is where pressure comes in. The stress that's placed on a crystal can change its orientation. It can change its direction of growth. This can include confining pressure. This is equal pressure from all directions, and directed pressure. This is pressure that's directed in two predominant directions. You're squeezing something, like squeezing a book between your hands, as opposed to squeezing an orange in your hand. The rate of increase is going to be 0.3 to 0.4 kilobars per kilometer depth. What this means, importantly, is that minerals are geobarometers and geothermometers. The presence or absence of certain minerals tell us about the pressure and the temperature at which a given rock may have formed. Here we have a pressure temperature depth diagram. We have depth on this y-axis, pressure on this y-axis, and temperature on the x-axis here. Starting at the surface, we're going to have a pressure of 0 and a depth of 0. Temperature is going to be Earth's surface temperature. Right now it's minus 26 outside. So in terms of absolute 0, around 250 degrees or 250 kelvins. So here we're going to increase the temperature by going further down into the Earth. In this temperature pressure regime, we're going to generate low-grade metamorphic rocks. Pressure is relatively low, and the depth is relatively low, as well as the temperature, all relatively low. As the temperature increases with increasing depth, we gradually reach high-grade metamorphic conditions. Here, we generally don't have rocks, metamorphic rocks, forming under these conditions. Temperature is not high enough. The pressure is certainly high. The depth is great, but the temperature isn't high enough to induce a change that we call metamorphism. Water can assist metamorphism when it comes from wet sediment or from clays. It can be attached or stuck to the surface. This is what you see when the surface tension allows insects to, water striders, to stay on the surface of water, or when water sticks to a container. You're pouring milk out of a plastic container and the milk runs down the side of the container instead of out of the container. Everyone's experienced it. Now, this is how water can get down into a metamorphic environment. It sticks to atoms, it sticks to clays, it sticks to other minerals. So these fluids are going to be important. They're going to lower the temperature of metamorphism. Metasomatism is the fluid transport of elements, resulting in a change in mineralogy and chemistry. So these fluids are also going to bring new ingredients to the pre-existing rock. This is going to increase the chemical reaction, lower the melting temperature, lower the temperature of metamorphism. When we look at a dual diagram like this, we can see a number of different types of metamorphic environments. Regional metamorphism is going to be the most common. It's forced by high temperature and pressure over large regions, usually at plate boundaries. We have some other examples here. Shock metamorphism is caused when a very fast-moving acorn strikes the Earth's surface, or bolide. An asteroid or a meteor hits the Earth's surface. That impact, that high heat and very high pressure, even though it's brief, is enough to induce shock metamorphism. We have large regions of rock exposed to higher temperatures and pressures. We will induce regional metamorphism. When we jam two plates together, here we have oceanic lithosphere, an ocean plate, colliding with a continental plate. We're going to generate high pressure metamorphism. This is going to be directed pressure in this case. And we can also induce contact metamorphism. When molten material comes in contact with country rock, it's going to heat that country rock and induce metamorphism within that country rock. We could have burial metamorphism if a sediment sequence becomes covered with sufficient material above to compress it. And at these higher temperatures with the higher pressure, we induce burial metamorphism. In the case of the seafloor, we have seafloor metamorphism, where we have cool water working its way down through fractures in the sheeted dike systems, becoming heated, picking up additional elements, additional metamorphic ingredients, and then working its way towards the surface again. This converts basalt into serpentinite as one example of seafloor metamorphism. So the contact metamorphism is caused by the heat from an igneous intrusion. Seafloor metamorphism is a result of hot seawater circulating through basalt, usually at mid-ocean ridges. Burial metamorphism is caused by deposition of overlying sediment, forcing rocks downward and compressing them. High and ultra-high pressure metamorphism are going to be rare at the Earth's surface because they require high and ultra-high pressure, which is not found at the Earth's surface. Therefore, these rocks are going to be found at great depths. Kimberlites and diatremes are examples of rocks that have erupted from great depths. We have some kimberlites here in Saskatchewan that are diamond producing, usually industrial diamonds, so small, not so attractive, but valuable nonetheless. If you remember back from the Howard Hughes story. The Hughes Corporation made a lot of money by embedding those cheap Saskatchewan kimberlite diamonds into drill bits. And a diatreme is kind of like dropping a Mentos in a Diet Coke. Very explosive, in fact, supersonic eruption. Shock metamorphism occurs when a meteorite collides with the Earth. The heat and pressure of the impact is going to alter the surface rocks, form very distinctive rocks, not only in terms of the mineralogy and the chemistry, but also in the shape of the shock metamorphic environment. Here we have an example of a shale that has been metamorphosed. And what you can see here are bedding planes. You can see it a little more clearly in the sketch. Bedding planes here are going to be ignored by this metamorphic rock. The cleavage is going to be in this orientation. It's not the same as the bedding plane. And the reason is there was pressure coming from this side, pushing this way, and pressure coming from this direction, pushing this way. The net result is the minerals become oriented relative to those stresses. That squeezing from right to left is going to induce the crystals to change their orientation, and in doing so, they change the cleavage of the rock. That's different from cleavage of a mineral. Foliation is the most prominent feature of regional metamorphism. It's the real giveaway in identifying a regionally metamorphosed sequence of rocks. A set of flat or wavy parallel cleavage planes is produced by deformation under directed pressure. So just like in the last diagram, we have a pre-existing sedimentary rock, the bedding planes here, here, here. This is being compressed from the right and from the left, and it's going to change the foliation. It's going to change the orientation of the crystals. Here we have starlight, that cross-shaped twin crystal we looked at before. Very distinctive metamorphic crystal. The presence of starlight indicates this is a metamorphic rock. The orientation or the foliation of the minerals indicates the pre-existing pressure regime. In this case, directed pressure. Taking a closer look, here we can see the minerals have transformed. They've gone from an orientation which would be horizontal in this image to one that is vertical. And again, that's because of directed pressure coming from this direction and this direction. And maybe a little more clearly illustrated here, the grains have recrystallized without ever melting. There is no melting, just a reorganization. And the net result is we have shale that's been converted into a metamorphic rock called a slate. When you look at a slate, say on the roof of a house, the shingles, that orientation of the slate may be perpendicular to the original foliation, the original orientation of the grains and minerals that made up that shale, the clays. So we're going to change the preferred orientation of the crystals. And in this case, we're going to develop slaty cleavage. And this is a function of foliation changing from the original bedding plane to one that in this case is perpendicular to that original bedding plane. Now, as we increase metamorphism, we're going to see a change in crystal size. We're going to see a change in the appearance of the foliation as well. So starting out with a shale, a sedimentary rock, we're going to bake it. We're going to increase the temperature and increase the pressure. So we're going to form a slate first. It's going to look like a shale, but it's going to be much harder. It's a baked shale. Much like you take clay and put it in a kiln and turn it into a pot or a bowl or whatever it is you're doing. You're changing the crystal structure. So increasing the temperature further, we produce a phyllite. A phyllite is going to look a lot like a slate, except when you hold it up in light, in the sun, for instance, you get a shiny, sparkly, glittery kind of surface. If we turn it up another notch, we end up with a schist. These have very large, very shiny, micaceous crystals. Increasing the temperature further, we develop a gneiss. These gneisses have fewer platy minerals. They're more blocky looking or sort of shoebox shaped. And if we increase the temperature just about to the point of melting, we end up with a migmatite. Looks like a swirly, toothpastey kind of rock. Whatever that toothpaste is, that has 3 colors. Whatever it's called, I don't remember. It looks like that. Here we see the crystal size increasing as the metamorphic grade increases. We also see an increasing coarseness of foliation from slaty, schistosity, the schistic look, a very shiny rock, banded rock of gneisses, and really twisted, contorted banding in migmatites. What do we use slate for? We'll start out with Clonfars in Gwynedd, North Wales. This is the old cog railway. A cog railway runs by a gear that's underneath this train, a coal-powered train, of course. And it chugs along with this gear like some kind of monstrous Lego device. This is the train reaching about 2/3 of the way up Mount Snowdon. That's the highest point in Wales. And you can see here the engine pushing the car up the hill. This is where they kicked us off because of the high winds. And that was actually much to my relief. This is the least comfortable train I've ever been on in my life. And somehow I ended up on it twice. It's basically putting you in a garbage can, beating you on the knees with a baseball bat, and rolling you down a rocky slope. Pretty much the feeling you get by hopping on this train. So what's this train here for? Why would anyone do this to themselves? Well, in this case, this was a train for the miners to reach the slate mine at the top of the mountain. You can see the tracks here working their way up to the top of Snowdon, which is in the fog here. And it's to get this stuff. This is slate. This is the old post office. It was built about 600 years ago, I think. And it has undergone some repairs, but you can tell that it looks like it was built about 600 years ago. So this is made almost entirely of slate. Its foliation allows you to split it into thin layers that can be used as shingles in this case. Now, slate is the lowest grade metamorphic rock. It's going to be colored by organic matter. So it's usually gray or black. It can also be red or green, blue, a number of other colors, depending on what type of organic matter and other minerals are mixed in. It's used for pool tables, used to be used for things called blackboards, flagstone, this would be kind of like sidewalks, and for roofing tiles. I happened to be in Greenland about 10, 12 years ago, and there was great excitement in Kulusuk. The pool table had arrived by airplane, and nobody knew what to do with it. So I helped carry the pool table in from the airplane and set it up in the pub. Got to play the first game of pool in East Greenland. Something to look back upon. Phyllite is going to be the next step up in metamorphism. It's got a glossy sheen due to the tiny micas that are present. Schist, another step up, displays schistosity. This is a coarse, wavy foliation, very shiny rock. Gneiss is going to be even coarser foliation, and this is because the light and dark colored minerals are increasingly segregated. There's going to be poor foliation. It's hard to split a gneiss, which is why they make countertops out of it. And it can grade into a very high-grade rock. Migmatites are going to be a mixture of igneous and metamorphic rock due to partial melting. It gives it that toothpastey look.